gonna be on Monday because we're pretty much almost gonna complete. Like we should finish chapter 5 today, definitely, and we're probably also gonna finish chapter 6 today. So we're almost gonna finish up chapter 5. Well, we're already gonna finish up chapter 5 today, and chapter 6. We might finish chapter 6 today. So I already posted up a study guide on Canvas. So let me show you where to go to get that study guide. All right, so here is Canvas. So we just scroll all the way down. For the study guide, you're gonna find study guide under week 5. So if you look right here, it says test 2 version A study. So it's a study guide for test number 2. All right. So right here, it's telling you all of the different type of topic that will be on the test. So you do want to kind of go over that for that way nothing should be surprising you if it does pop up on the test. So just make sure that you go over all of these and you just kind of go over them to make sure that you understand all of this or you kind of have a good idea about these questions. All right. Any question on where to find the study guide? Wait, all right, so let me stop this share. Oh, the study guide bot? Yeah, I probably did that. No, the study guide should be open. Remember, it should be called Test 2 Version A Study. If you click on Test 2, that one is locked. You want to click where it says Test 2 Version A Study. That one should be open. All right. Any question in regard to the study guide? Okay. Edit. All right, so week 5 should be open. I forgot that I put that on a date, so it should be open. If you're trying to figure out where the annotated notes are, well, let me show you. La, 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 la. If you go to Canvas, if you look right here, it says annotated notes. You click on any one of these, and those are their annotated notes. All right. Any other questions before we get started with chapter 5? Sure. Let's see. Exit. Wait. Oh, shit. All right, so test 2, the homework, all of it is due on blah, 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 on July the 13th. So all of that should be fixed now. All right, so you already know the homework is due on July the 13th. Test 2, you're gonna have test 2 on July the 13th. I already unlocked all of the other weeks, so if you are wanting to print out the notes, you could definitely already do that. All right. Sweet. Any other questions before we get started? All right, so let's go ahead and finish up chapter 5. Chapter 5, we don't have that much left. Should be pretty fast, hopefully. All right, so this is where we left off for chapter 5. So if you look at right here, I put combos because essentially this is where you kind of want to be mixing in some of the different like counting technique and the combination rule, or you might want to be using permutation rule and the counting technique. So for this one, you're actually going to be using multiple different combination rule, or combination rule with the counting technique, or combination rule and permutation. So we're going to be mixing stuff up. So for this one, said a physics exam consists of 9 multiple choice questions and 6 open-ended problems in which all work must be shown. If the examinee must answer 5 of the multiple questions and 4 of the open-ended problem, in how many ways can the question and problem be chosen? All right, so if you look at this one, you have 2 different types of problem. We have multiple choice, and we have open-ended question or problem. So for the multiple choice, how many different multiple choice questions do we have? Oh yeah, let me put it in the chat. Wait, all right. So 10, 9. So we have 9 multiple choice. What about open-ended? Open-ended, how many open-ended questions do we have? Let's try that again. There you go. So we have 6 open-ended questions. All right. Everybody good for 9 multiple choice question and 6 open-ended question? So it says if an examinee must answer 5 of the multiple choice question and 4 of the open-ended problem, in how many ways can the question and problem be chosen? So for this one, kind of think about it. You have a test and a quiz. So for this one, you don't have to answer all 9 multiple choice questions. You also don't have to answer all 6 open-ended questions. For the multiple choice question, all you have to do is answer 5 of them. For the open-ended question, you only have to answer 4 of them. So for this one, we could say pick 6. Oh, sorry, pick 5. And we pick 4. So what we want to do, we kind of want to figure out, is this a permutation or is this a combination? So for this one, does it really matter like the order that you answer the questions? Or is it pretty much just like you pick whatever question you want to do? Yeah, so for this one, like the order doesn't really matter. So for this one, you want to do a combination. So you could do 9 choose 5, and we could do 6, choose 4. Because this is going to tell me of the 9 questions, how many different arrangement can I get where I answer 5 of them. Same thing for the open-ended question. For the open-ended question, it could go like, there's 6 open-ended questions, and we want to see in how many different ways can I choose 4 of them. So maybe I pick the first 2 open-ended questions and the last 2 open-ended questions. So the order really doesn't matter. So right now, what I'm going to go ahead and do, I'm going to use the TI-84 just to solve this out for me. So let's say 9, C5. So for the multiple choice, there's 126 different combinations that I could choose from. So saying like, depending on which 5 I choose, it's telling me there's 126 different ways that I could choose 5 questions. So you get 126. So let's do the open-ended question. For the open-ended question, we have 6C4. So I'm gonna go back to my TI-83 or 84. Well, in my case, I don't know what it is. You go 6, math, PRB, and 4. And I get 15. So you get 15. All right. Any question where the 126 come from, or where does the 15 come from? All right. So the last step what we want to do, because I don't want to find out how many different arrangement can I have for multiple choice and how many different way can I have open-ended question. I want to know for the entire test. So pretty much what we have to do, we get whatever we got for multiple choice and you multiply by open-ended. And that's going to give me all the different versions or all of the different ways that I could choose 5 multiple choice with 4 open-ended question. So what we're going to do now, I'm going to do 126 times 15. So 126 times 15. And you get 1890. So there's 1,890 different ways that I could choose 5 multiple choice questions and 4 open-ended questions. And that's it. So if you kind of look in the beginning, we're doing the combination rule. But when we're doing this portion right here, when we multiply these two, we're pretty much doing the counting multiplication rule. And that's it. All right. Any question for that first problem? All right. So let's go on to the second problem. So the second problem says, in how many ways can a committee of 3 men and 4 women be formed from a group of 9 men and 9 women? All right. So we're going to construct a committee. So for the committee, we have our men and we have our women. So for the men, how many seats do we have for the men? Like how many men do we want in the committee? Cool, 3. So that means we have 3 spaces open for men. So 1, 2, 3. What about for women? How many women do we want in this committee? 4. Perfect. Thanks, Stephanie. 2, 3, 4. There you have 1, 2, 3, 4. All right. But how many men do I have to choose from? 9. How many women do I have to choose from? So for this one, does it matter on which of the women or which of the men get chosen first? Or does it really not matter because at the end of the day, they're all going to the same committee? Cool. Doesn't matter. So it doesn't matter. So that's why we're going to do combination. So for this one, we're going to say 9. And we want to choose 3 of the men. Same thing for the women. We start off with 9. Sorry. And you want to choose 4 of them. So I'm going to go ahead and use my calculator. So calculator, you go 9, math, PRB, NCR, and we do 3. So you get 84 for the men. So 84 for the men. So it's a 84. So that's 84 for the men. I'm going to go back and now I'm going to do it for the women. Oops. Nope. So if you look at this, I'm going to copy and paste and you change this from a 3 to a 4. And let's press enter. I get 126. All right. So that's how many ways I could choose 3 men of the 9, and that's how many ways I could choose 4 women of the 9. But the thing is, I want to find out how many different combinations can I have for this group of committee or this committee group. So what we have to do, we have to get the 84 and the 126, and we have to multiply them times each other. Because this is going to tell me the different way that we can have it. So depending on the 9 distinct men, it's going to tell me the different way that we could arrange them, or the 9 distinct women. So somebody already gave me the answer. Let me double check it. Cool, good job, Stephanie. So you get 10,584. All right, so those are how many different ways we could make a committee of essentially 7 people, where we have 3 men and 4 women. All right. Any question in regard to the last problem? All right, so let's do this one, and then I'm gonna want you to try out this problem. We'll do some breakout room for this one. We'll have some fun with it. Okay, so it says in poker, how many ways can you get 3 aces and 2 threes? Cool. So essentially, we want to find out how many ways can we get 3 aces and 2 3. Oh, all right. So we just want to find out how many different ways you could get 3 aces and 2 3. So that's a pretty good hand. That's a full house. So pretty much we want to find out how many different ways can we get a full house where you get 3 aces and 2 3. So for this one, kind of you think about it, like for this one, this is one of the ways you could get it, but does it make a difference if I get ace 3, ace 3, ace? Like, is the first one completely different from the second one? No, because for this one, it really doesn't matter if you get ace, 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 3, 3, or if you get ace, 3, ace, 3, ace. It's still 3 aces and it's still 2, 3. So for this one, it's combination. So, all right. So if you don't know about poker hand or anything like that, I put a little cheat sheet right here. So if you look at how many aces I have 1, I have 2, I have 3, and lastly, I have 4. So I have 4 aces. So let me go back. Oh my God, why is it so slow? So right here, I have 4 aces to choose from, but how many aces do I actually want to pick? Because I don't want all 4 aces. How many aces do I want? 3. Good. So we'll put right here, ace. All right, what about for 3? Oops. I don't wanna do that. So there you go, also 4. So you go 4, C, but how many 3 do I want to choose? 2. So we put 4C2. Everybody get how I got 4C3 and 4C2? Okay, so let me go to my calculator and do this. There you go, 4, math, PRB, NCR, we do 3. Here, let me also do 2 while I'm here. All right, so you get 4 and 6. So this is 4, this is 6. So if I do 4 times 6, you get 12. Oh, no, that's some bad mental math. You get 24. Yeah, sorry about that. All right, but that's it. No new math, just forgetful math. All right. So if you look at these the problems are not that hard to do. Like one thing you have to know like where in your calculator you have to go. So like going to math and then going to PRB and then going to NCR or NPR, that should be pretty fast for you because if you're kind of taking time with that, it's gonna slow you down. So you do kind of want to know like, okay, how do I get to NCR, NPR? So in a sheet of paper, if you are struggling on how to get to NCR or NPR, you might want to write down some instructions there for that way you don't get stuck and that way you kind of know where to go. All right. Everybody good for this last problem? All right, so let's try this one. All right. So I don't want to scare you on this one, but this is going to be a combination of the counting technique. It's going to be a combination of the multiplication rule for dependent events. So we're going to be pretty much combining what we learned in 5.5 and combining what we learned in 5.4. So this is going to have everything mixed together. So for this one said the iPhone has 4-digit code where each digit has a number from 0 to 9. It is okay to use the same number multiple times for the code. All right. So for this one, you should already know this is not permutation, this is not combination. Why is this not permutation or combination? Exclamation mark. Perfect, good job. So the reason why this is not permutation or combination because it tell you could get the number and they can actually repeat. So as soon as they tell you the number can repeat, automatically you should know this is not permutation, this is not combination, this is pretty much the counting technique. All right. So for part A, it says how many different codes are possible for the iPhone? So how many different codes are possible for this iPhone? Like how can I find that? Well, remember, we just said we can't use combination because the number can repeat. Cool. Thanks, Lauren. So if you look at what Lauren got over there, oh my God. Let me kill this pencil. First, second, third, and 4, 10, 10, 10. Why is it taking so long? What the lag? So if you look at it, you have the first digit, you have the second digit, you have the third digit, you have the fourth digit. For each one of them, since you could choose a number from 0 to 9, from 0 to 9, there's actually 10 digits. So pretty much each time I choose a digit, I have 10 numbers to choose from. So what we're going to do, we're going to say 10 times 10 times 10 times 10. So if I do 10 times 10 times 10 times 10, we get what? Cool, 10,000. So we get 10,000 different passcode. So let's do part B. So for part B, it says, what are the probabilities some random person will guess the correct code? So yeah, in that case, you could then use, well, not the factorial, but you want to use the combination. Or sorry, you want to use permutation, because in this case, order does matter. Because if I put 2 right here, like that does make a difference, because pretty much the passcode will only work if you put 2. So you do want to use permutation if it says that pretty much no number is repeating. All right. So what are the probability that some random person will guess the correct code? Yeah, good. There you go. 1 out of 10,000. All right. I'm not even gonna try to attempt that because it could be super small. All right, so part C says the iPhone will give a person 3 tries to unlock the iPhone. After the third attempt, the iPad. I went from an iPhone to an iPad. Oh, my bad. So the iPhone will self-destruct. So what is the probability the iPhone will self-destruct if a random person trying to guess the correct code? Oh. All right, so for this one, how many attempts does the person have to guess correct? 3. So for this one, is the person had multiple attempts, correct? So since the person had multiple attempts, which rule should I use? Start with an M. And it ends with rule. There you go. You want to use the multiplication rule because pretty much you want the first attempt, you want the second attempt, and you want the third attempt. So for this one, we want the iPhone to self-destruct, correct? So the iPhone only self-destruct when they guess it incorrect. So what's the probability that the first attempt is incorrect? There you go. Good job. So 999 out of 10,000. So that's the probability that somebody will guess the password incorrect. So it's kind of telling you like this person is not gonna guess it correct in the first try. All right. So let's go on to the second try. So for the second try, what's the probability that this person guessed it incorrect the second time. I'm gonna give you a hint. It's not the same as the first one. You're almost close. You just have to finish it out. Almost close. You're missing one thing. There you go. Thanks, Julian. So you get 9,998 divided by 9,999. So, okay, you have to kind of think about it, like, since I already tried one passcode the first attempt, like, if you're smart, you're not going to use that same passcode again. So that means there's one less passcode that is incorrect, but there's also one less passcode to attempt. So essentially everything goes down by one. So instead of saying 9,999, you say 9,998. Instead of saying 10,000, you should say 9,999. All right, lastly, let's do the third attempt. So for the third attempt, what should be the probability for the third attempt? Good job, Stephanie. 9,997 divided by 9,998. All right, everybody go with these fractions. All right, so before you actually go out and start multiplying them, what you want to do, you want to simplify. This is one case where you could simplify. This, simplify this, simplify this, and we get 9,997 all divided by 10,000, which is equal to 0.9997. So there's a pretty good chance that if somebody just randomly guessing your your passcode for your iPhone, that is most likely going to self-destruct because it's almost 100% chance of that occurring. And that's it for that last problem. Any question for that last problem? Wait. And that should be it for chapter 5. I think this, yeah. Here are the cards. Oh. All right, we're all done with chapter 5. So no more chapter 5. Any question in regard to chapter 5 before we move on to chapter 6? All right, let's move on to chapter 6. I know. Chapter 6 should be a quick one. And chapter 6 is kind of like piggybacking off of chapter 5. So if you kind of like the multiplication rule, chapter 6 is kind of going to give you a shortcut for the multiplication rule. Okay, so let's get started with chapter 6. Chapter 6, first thing you have to kind of know, you got to know the difference between discrete random variable and continuous random variable. So if you look at my data set, I put an illustration, well, I put a graph up. So if you look at my discrete random number, what do you notice about the red dots? So what do you notice here about the red dots? The red dots are only where? Whole number. So if you remember, discrete numbers are only for whole number that are countable. So I should be able to say 0, 1, 2, 3, 4, 5, so on and so forth. For a continuous data set, which is this one, what do you notice about the red line? It's where? Well, if you look at the red line, it's pretty much all across or it's everywhere. So that means for continuous data, there is no limitation like between here and between here, there technically infinite many numbers between those two segments. Because no matter where do I cut the two segments, if those are continuous data sets, technically they're always infinite many data sets. So if I were to cut this one up, there's infinite many numbers here. All right. So anytime you're looking for discrete data set, always kind of think about, is it possible that it's in between 1 and 2? If the answer is no, it can't be in between 1 and 2, it's discrete. But if you go like, is it possible it could be between 1 and 2, and the answer is yes, now that's considered to be continuous. Because continuous is whenever pretty much you have, like one thing that students always get continuous with, they think continuous means it keeps going and going and going. Like if I tell you how many stars are in the sky, well, technically, you can keep on counting and counting and counting. You keep on going. But when you think about how many stars are in the sky, can you count that? Or that's something where you go like, okay, that's half of a star, that's a quarter of a star. Like, no, it should be like either you have a star or you don't have a star. So that would be considered discrete data set. So just remember, discrete data set just means you can actually count it, and it's not possible to get any partial. Versus continuous data set means, yes, you could get those values, but you could get values in between those two values. All right. Everybody good so far with the definition of discrete and continuous? All right, so let's do these examples. So all we want to do is say, is it continuous or is it a discrete variable? So for part A, it said the number of light bulbs that burned out in a room of 10 light bulbs in the next year. So would that one be continuous or discrete? Cool. All right, good job. Everybody said discrete. It is discrete. What about B, the number of green M&M in a bag? So once again, that would be discrete because you can count that. What about the length of time between call to 911? Wait, continue. How about how many coins a person has in their pocket, if a person has coins anymore? Good, discrete. Yeah. All right, what about the distance from here to the moon? Like the way you could think about continuous, if you actually had to measure it, because if you look at the length of time between call to 911, you actually had to measure how long had it take. If you look at the distance from here to the moon, you actually have to measure. But if you look at how many coins a person has in their pocket, that's something that you could just count. You don't really have to measure it. You could just go like, okay, they have 1 coin, they have 2 coins, they have 3 coins, so on and so forth. All right, so let's do this next one. So this is kind of a repetition of something that we already did. So this is the rule for discrete probability distribution. So this is the same rule that we used when we did chapter 5. Because if you remember that rule where we say, if you add up all the probability, they should add up to 1. And lastly, if you have all of the probability should be between 0 and 1. So this is a rule that we used when we did in chapter 5. I'm just reintroducing it. So for this one, nothing new technically happened. This should be something that you should already know. So for this one, it says, is the following table a probability distribution? So to check it, to see if it's a probability distribution, we have to check both of these. So let's check this one off. 0. If you look at all of the probability, do we have a probability that's above 1 or below 0? No, so all of these checks out. And just remember the X value, well, we don't care about the X value. You're not looking at the X value. You're only looking at P of X. So that checks out. So let's check out the next one. If I sum up P of X, do they add up to 1? So if I do 0.06 plus 0.58 plus 0.22 plus 0.10 plus 0.03 plus 0.01, what do they add up to? 1. So we say this is a probability distribution. Any question for that last problem? So let's go on to this one. So for this problem, it should literally take you 1 second to already know that this is not a probability distribution. Why is this not a probability distribution? Cool. And that's it. I'll say not a probability distribution. As soon as you see the negative, you should already know this is not a probability distribution, and that should be it. Like this problem, you shouldn't even last 2 seconds on it. If you last 2 seconds, more than 2 seconds on it, you're wasting your time. All right, what about this one? Is this a probability distribution? Yeah, because if you look at it, technically all of the probabilities are between 0 and 1. So that checks out. If you add up the probability, they add up to 1. So say this is a probability distribution. Okay, if you do 0.25 plus 0.25 plus 0.25 plus 0.25, well, you get 1. Everybody good with that last one? So up next, we're getting to something called the mean. Hopefully you have heard of this. We saw the mean in chapter 3. So back when we did the mean for chapter 3, we had all of these numbers. And in order for us to calculate the mean, you went 3 plus 4 plus 5. You divide it by however many numbers you have, which was 3. And if you did that, you got 4. All right, so that's how we used to do it for the mean. But what we're gonna do right now, we're gonna do it for when I don't know exactly how many numbers I have, but I know how many times those events occur. So if you look right here, it says you get x and you multiply by p of x. Once you multiply x times p of x, you sum it up. So that's what we want to do because pretty much the p of x is telling us how many times are these number happening. And the x is telling us like, okay, pretty much x is occurring this many times. So let's go ahead and do this problem. So it says example to find the mean for a discrete random variable. So it says organizer of a concert are limiting tickets sold to a maximum of 4 tickets per customer. Let T be the number of tickets purchased by a random customer. Here is the probability distribution of T. So I want to change this to capital T. All right, so if you look at T, T is represent how many tickets somebody purchased. So obviously for this one, we didn't put 0 because we don't have any data set for how many people purchase 0 ticket. We only have data set for how many people purchase either 1 ticket, 2 ticket, 3 ticket, or 4 ticket per customer. All right, so if you look at this one, we have that a person or a customer bought 1 ticket, and that's 10% of our data set. So 10% of our data set bought 1 ticket. So if you look at our data set, which one got the most, well, how many tickets were most sold? 1 ticket, 2 ticket, 3 ticket, or 4 ticket? Yeah, 4 ticket, because if you look at 4 ticket, that got 40% versus 3 ticket, which got 20%, versus 2 ticket, which only got 0.3 or 30%, so on and so forth. So let's do x times p of x. So if I do 1 times 0.1, you get you get 0.1. If I do 2 times 0.3, you get 0.6. So I'm getting this number by doing 1 times 0.1, 2 times 0.3. If you do 3 times 0.2, you get 0.6. If you do 4 times 0.4, you get 1.6. All right. Any questions so far on how I got 0.1, 0.6, 0.6, and 1.6? All right. So the last thing we're going to go ahead and do, we're going to sum it up. So we're going to say mu of x is equal to 0.1 plus 0.6 plus 0.6 plus 1.6. If I do all of that calculation, you get, what do you get? 1.2, 2.8, 2.9. Cool. So you get 2.9. So 2.9 is my average. So on average, if somebody is buying tickets for, well, a concert, on average, they buy 2.9 tickets. But if you kind of look at it, it's kind of impossible for them to buy 2.9 tickets. Like either they bought the entire ticket or they bought some of it, or they didn't buy the ticket. So for this one, we could say on average, they buy 3 tickets. And that's it. Any question in regard to how to find the mean for that first problem? All right, let's do the second problem. So for this one, says example, find the mean for a discrete random variable. The Bank of America VP feel that each saving account customer has on average 3 credit cards. The following distribution represents the number of credit card people own. Let's see. So if you look at it, it says a person can have 1 credit card, 2 credit card, 3 credit card, and then it's you stop at 4 credit card. All right. So we're gonna go ahead and we're gonna go ahead and just get the multiplication. So if I do 0 times 0.18, what will that give me? Well, does it make sense when I do 0 times 0.18 that it give me 0? Yes, no, maybe. Well, why does it make sense?
Because any number multiplied by 0 equals 0.
Well, we're kind of, well, that's technically, yeah, the multiplication of like multiplying by 0 will give you 0. But if you kind of think about it, If you kind of think about it, this is telling me 18% of the population doesn't have a credit card, correct? So that means if I go to 18% of the people, so say if we have 100 people, of 100 people, 18 people don't have a credit card. So that means I'm going to be getting 0 and then getting another 0. So if you do 0 plus 0 plus 0 plus 0, you get 0. So that's why pretty much whenever you have x is equal to 0, this will always yes be 0. All right, what about for the next one? 1 times 0.44, what do we get? 0.44. What about 2 times 2.7 or 0.27? Sweet, 0.54. What about 3 times 0.08? 24. Lastly, what about 4 times 0.03? Sweet. So then if I want to find the mean, you get 0 plus 0.44 plus 0.54 plus 0.24 plus 0.12. All right. If we add all of those numbers up together, what do we get? All right, we got 1.34. So say mu of x is equal to 1.34. All right, so this is telling me roughly people on average have 1 credit card or 2 credit card. Because since it's 1.34, it's in between 1 and 2, so we could say it's between 1 and 2. Everybody good for that one? Okay, so now we're gonna be going from the mean and we're gonna be going to the expected value. So the mean and the expected value are exactly the same thing. There's no difference between the mean and the expected value. It's essentially, yes, different notation, but pretty much when we find the mean and expected value, kind of if you look at the word expected like what we expect to happen. Same thing with the mean is just the average, just telling us like this is the average number because this number happened the most often, which is expected. So whenever you see the mean or expected value, just know both of them are exactly the same thing. To calculate the mean or the expected value is the same way. You multiply the x times the p of x, and then you add the numbers. All right. Everybody good for mean and the expected value? All right, so let's have some fun with this. So it says a term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. The policy have premium that must be paid annually. Suppose the life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old male for $530. According to the National Vital Statistic Report, the probability the male will survive the year is 0.99791. Compute the expected value of this policy to the insurance company. Alrighty then. So if you look at this one, they gave me a lot of information. So we kind of want to look at all the number and try and make sense of all of these numbers. So let's make sense of the easiest one. What does the 0.99791 represent? So this is the probability somebody survives. So 0.99791. All right. Everybody get probability that somebody survive is 0.99791. Alrighty then. So what does the 530 represent? Well, right now, I don't want any X or P of X. All I want to know, like, just tell me what does that mean. Well, is the cost of the insurance cool. All right, so that's the cost of the insurance policy. Perfect. What about this $250,000? What is that? Well, not exactly. So if you look right here, it says suppose the life insurance company sell a 250,000 1-year term life insurance policy to a 49-year-old male. So pretty much this is the payout. So if this 49-year-old male dies at the end of the year or somewhere in between, pretty much this $250,000 get payout to whoever is the beneficiary of this life insurance. So this is the payout. So the payout is equal to 250,000. All right, so we know what's the probability somebody survive. We have the cost of insurance. The cost of the insurance policy is $530. And we know if the 49-year-old male does die, how much the beneficiary actually get from this life insurance. They get $250,000. All right. Everybody good with that? All right, unanimous? Yes. All right. So up next, what we're gonna do, if you look at my notes, I have a table. So the table says survive, does not survive. It says X and it says P of X. So the X correspond to the money. So it corresponds to the money, but for this one, you always have to look at who are we doing the expected value for. So for this one, are we doing the expected value for the person buying the insurance, or are we doing the expected value for the insurance company? So we're doing this for the insurance company. So that make a huge difference because now instead of our expected value being maybe positive, instead of our expected value being negative, it's most likely going to be a positive because depending on who viewpoint you find the expected value, it's either going to give you a negative or it's going to give you a positive, or it might even give you like a 0. So you do have to always look at who are we doing the expected value for. So for this one, we're doing it for the insurance company. So first thing we're going to do, we're going to do P of X. So we're going to do P of X. So let's fill out this one. So what's the probability somebody survived the year? Cool. 0.99791. Great job. All right. So what's the probability somebody does not survive the year? Cool. So you want to do 1 minus 0.9979, 91, which Javier already gave us, is 0.00219. Sweet. So for this one, if you kind of remember back when we did mutually exclusive, these two events are mutually exclusive because you either survive or you don't survive. There's pretty much no in between about this. You can't survive and not survive at the same time. It's either you survive or you don't survive. There you go, complementary rule. All right, everybody good for that? All right, so P of X, usually P of X is the easiest part. What students tend to have a hard time is getting the X value. All right, so let's do the X value. So we're gonna do the X value and we're gonna do this for survive. So remember, we're doing this for the insurance company. So if the person survived the entire year, how much money does the insurance company get? Oh. Ooh. All right. There's a little typo right here. That one should be 0.9. Cool. Thank you. No, it's not monthly. It's essentially for the entire year. All right. So everybody got it? It's 530. And the 530 is not, if you look at it, it says 530. It doesn't say monthly or anything like that. So pretty much for this one, where you get take it as is 530 and you have the life insurance for the entire year. All right. Everybody good for 530 for survive. All right, everybody good for 530 for survive. So let's go ahead and do does not survive. So if this person does not survive, is the insurance company, are they gonna pretty much get money or are they gonna lose money? Cool. So they're gonna lose. How much are they gonna lose? So they're gonna lose $250,000. But the thing that you have to kind of understand, they're not out all that money because remember they still have his $530. So we still have that $530. So what you have to do 530 because that's what they pay for it. So if we do have to pay out, it's essentially the net difference of that value. So have you already put it up? So it should be negative 249,470. And that's it for that. So remember, you're always doing the net loss. You're not doing just the loss, you're doing the net loss because you have to see how much money have they already retained and you have to see how much money did they lose. And then you have to see what the net of that value is. And then that will be your net loss for does not survive. All right. Everybody good with that? So everybody good? I got negative 249,470. All right. So let me do some cleanup. All right, so if you remember the formula to how to find the mean, it's the same formula for the expected value. What you do, you get the x value, multiply by p of x, and then you add those values up. So we get 530 multiplied by 0.99791, and we do the same thing for this one. So we're gonna do 530 times 0.99791 plus negative 249,470 multiplied by 0.00209. All right. Any questions so far on how I got 530 times 0.99791 plus a negative 249,470 times 0.00209? Fantastico. All right, so up next, I'm going to show you how to do this in the TI-84. So we'll say new share. Oops. Let me get the TI-84 going. That didn't work. Let's do new share again. There you go, TI-84. All right, so for the TI-84, you do 530 multiply by 0.99791 plus, if you look at the button right below the 3, that's a negative sign. So you want to use the button right below the 3 to represent that it's a negative. So you put negative 249,470 multiply by 0.00209. If I get that, you get 7.5. So you get $7.05. Right. Everybody go with those $7.05. Cool. All right. So let's kind of go into like, what does that $7.05 represent? So you kind of have to think about it. That's the average, but it's not the average for one person. Because if you kind of think about it, like, if they sell this policy to one person, if that one person dies, then they're screwed because they didn't get that much money from everybody. Because if you remember the law of large number, it pretty much worked the same way. The $7.50 represent the law of large numbers. So saying if I sell this policy to many, many, many different people, pretty much I'm not expecting everybody to die. You probably, like, if you sell 100 of these, probably only one person is gonna die. So you're hoping that the 530 that everybody else is paying you will cover that one person dying. Because pretty much what you want there to be a net income where you go, like, you're collecting $530 from everybody else, and with that money, you should have enough money to cover if one person die or if two person die. So for this one, is saying on average, if you sell this to many, many, many different mail, on average, each mail they're gonna get $7.50 back. But they do know like they're gonna lose a couple of times because they do know like some people are not gonna survive the entire year. But with the other hundreds or thousands of people, that should overcome the one loss of a person. All right, but that's it for that first problem. Any question for that first problem? All right, let's do the second problem. So this second problem has nothing to do with anybody dying, so it should be a fun example. Cool. So if you look at the problem, it says a lottery ticket costs you $5. 5,000 lottery tickets are sold with a payout of $5,000. What is the expected value for the person buying the lottery ticket? So when you're buying a lottery ticket, what are the two outcomes that could occur when you buy a lottery ticket? Cool, win or lose. So you can either win or you can lose. So what is the probability that somebody will win? Well, in this case scenario, what's the probability that somebody win the lottery ticket? Or somebody has the winning lottery ticket? Good. It's 1 out of 5,000. So for this one, be careful. We're talking about this 5,000, not this 5,000. We're talking about the 5,000 lottery ticket that were sold. So we know they sold 5,000 lottery ticket and only one of them is a winner. So that's why the probably somebody winning is 1 out of 5,000 because we're assuming they buy one ticket. So they have 1 in 5,000 chance of winning. All right, so if they have 1 in 5,000 chance of winning, what are the chances that they lose? Good, perfect. 4,999 divided by 5,000. So complementary events again. So you either win or you lose. There's no in between. So all you have to do, you do 1 minus 1 divided by 5,000, and you get 4,999 divided by 5,000. Right. Everybody good for P of X, for win and for lose? All right, let's do our X value. So what is the probability, what is the X value if somebody, let's do if somebody loses. So if they lose, how much money are they out? All right, so for this one, you want to put -5. The reason we're putting -5 because we're doing the expected value for the person buying the lottery ticket. So since we're doing it in the point of view of the person buying the ticket, so if they lose, they're out the $5. But what happens if they win? If they win, how much do they win? Good. They say 5, no sir, get away. So you get 5,000 minus 5, and you get 4,995. Cool. So remember, they're not gonna win the entire $5,000. Yes, at the time you think they win the $5,000, but remember they had to pay $5 in order to win that $5,000. You kind of think about it. Say like for people who buy like a lot of lottery ticket, and they buy like 500 lottery ticket for $1, but they only win $400. Yeah, they won $400, but they wasted $500 to get those $400. So they actually didn't win. They actually lost $100. So you always have to think about it in that way. All right, everybody good on how I got this so far? All right, so remember, in order to find the mean, we use the multiplication rule. So multiply. They get 4,995 multiplied by 1 divided by 5,000. And then you add it to -5 times 4,999 divided by 5,000. All right, so let me go ahead and transfer over to my handy TI-84. And let me go ahead and do that. So you get 4,995 multiplied by 1 divided by 5,000. Plus a -5 multiplied by 4,999, all divided by 5,000. If I press enter, you get -4. Everybody got how I got -$4? All right, so let me go back to this. All right, so I get the expected value is equal to -4. So that you're saying like, hey, like we're not you're gonna be playing this lottery one time. If you play this lottery like many times, like eventually you are gonna win. But by the time that you win, you're gonna have paid $5 to play this lottery. That the amount, kind of like the amount that you pay to play, it's gonna outweigh how much money you actually won. So at the long run, you're essentially going to be losing money versus earning money. Kind of if you ever gone to Vegas, sometime when you go to Vegas, you win. Sometime when you go to Vegas, you lose. But what usually happens more, you lose more compared to than when you win. So essentially, the expected value will always be a negative for you because you're going to lose more than you actually win from Vegas. All right. And that's it for that one. Any question in regard to the last prompt? All right. So the last thing we're gonna do, let's actually skip D. Let's do C. If you want to do B, you could go ahead and do B. It's the same thing as the first one. So let's go ahead and do this one. So this one for iPhone. So we'll say the iPhone 100 has a 15% chance that their screen will break. If the warranty for the screen costs $10, it costs Apple $159.99 to repair the broken screen. So it says, what is Apple expected value on the warranty? So if you ever had a phone, most of you, some of you probably have experienced that you break your screen. So you kind of want to determine like, okay, when did it suit you to buy the warranty? When did it suit you not to buy the warranty? But they kind of go based off of person to person, because if you're one of those person that always breaks your cell phone screen, you might want to get it. If you're one of those person that hardly never break your cell phone screen, you probably don't need it. So kind of you go based off person to person. But for this one, we're going to generalize and you say like 15% of all cell phone or iPhone will break. So let's do the table. So we'll have this. We'll have this. We'll have this. So we'll say X. We'll have P of X. All right. So when you buy your cell phone, what are the two options that could occur for the screen? Wait, all right, break or doesn't. So we'll say break. We'll put the complement symbol for don't break. So what's the probability my cell phone or the iPhone 100 will break? All right, so we put 0.15. Also, just a point of advice for the P of X, it should always be in decimal, because if you do X times the percentage, this formula is not going to work. It has to be in decimal form. So heads up. All right, what's the probability that the phone would not break? 0.85. Cool. All right, so for this one, who point of view are we doing this for? Are we doing it for the point of view of the consumer buying the insurance, or are we doing this for Apple? So we're doing this for Apple. So when is Apple gaining money? Like they're always gaining money, but in this case scenario, when are they gaining money? Cool. So when it doesn't break, if it doesn't break, that means you pay for the warranty, but you're not actually using the warranty, so they get to keep that money. So they get to keep $10 for doing absolutely nothing. So 85% of the time they keep $10. All right, but that's not always the case. So what happens if the cell phone screen break? Are they gaining money or are they now losing money? They're losing. How much money are they losing? Perfect. Negative 149 with 99 cents. So up next, you multiply these. All right. Here, let me distinguish that. Everybody good so far with what I have on the table? Yes. Wait. All right. So up next, what you want to go ahead and do, you have multiply. So we do 10 times 8, oops. So say 0.85 plus a negative 149.99 times 0.15. So let me go ahead and do my TI-84. TI-84. So we say 10 times 0.85 plus a negative 149.99 multiply by 0.85. And if you multiply that out, so we get expected value is equal to negative 118.99. And we'll cut out to 2 decimal places since we're dealing with money. Like it wouldn't make sense to get 99 cents and then 15 tenths of a cent. I don't want to do that. So we'll say negative 118.99. Everybody good on how to find 118.99 on their calculator? All right, so let's go ahead and move over back to the notes. All right, so for this expected value, is this good news for Apple or is this bad news for Apple?
Good news.
Why would it be good news though? Well, if you look at it, because we're doing this expected value in the point of view of Apple. So in Apple point of view, they're losing $118.99 every time they sell this cell phone. Because essentially it's saying we're pretty much, well, for this one, what's happening? Like, why are they losing money? Or why do you think they're losing money? Any business major here? Well, what about the repair? Well, that, but also let's look at the other thing. How much are they charging for the warranty? Well, aren't they only charging $10 for the warranty? Well, remember, it's $10. So for this one, it's not $10 per month. I know they have that now or anything. This is just a $10 flat fee. So it's kind of telling us that this warranty is too small. Like they're not collecting enough money to cover this warranty. So what they want to do, okay, if you look at the question right below, it says, should they adjust the cost of the warranty? The answer should be yes, since they are losing money. Yeah, because pretty much every time you have to replace a cell phone, they're essentially losing money because they priced their warranty too low. So if they want to adjust it, they could either adjust their warranty where they could charge them more for their warranty, or they could pretty much they could go and then say maybe they could try to get the price of the repair to get lower, or they could just make cell phone that doesn't break their screen. But yeah, but for the easiest solution for them, all they have to do is just raise the warranty. So instead of charging $10, they might want to charge like $50 or $100.
I have a question.
Yeah, Julian, what's up?
Does it matter how you set up this addition equation? So for example, let's say I take the negative 149 first, and then I do the second equation. Does that matter?
No, I'll do it right now. It should not matter. So like for the negative, so you put negative 149 with 99 cents, and that's multiply by 0.15, and then you add it to 10 times 0.85. I think I know what I did wrong. Oops. This should be a multiplication symbol. I forgot the decimal. Here, let's do this again. So again, negative 149 with 99 cents multiply by 0.15
plus
$10
times
0.85. Yeah, I think I know what I did wrong. Yeah. No wonder we're getting so many angry chats. The negative 13.9985, which essentially just round up to be negative 14. Yeah, sorry about that. I think I put where I said negative 149.99 times, I multiplied times 0.85 versus 0.15.
Oh yeah, no problem. Just making sure.
Yeah.
Thank you.
But yeah, it doesn't matter if you switch them around. Like you should still get the same answer as long as you use the right decimal value. All right. Everybody good for that last one? So here, I'll give you the answer for it. All right, so this is the new answer. So if you look at it, it's negative 13.9985, but essentially this A is going to round up this 9, which is going to round up this 9, which just round this up to $14. And that's it. All right, so they're losing $14 every time they sell this warranty, which sounds a little bit better versus $100 and something. All right, everybody good for this last one? All right, so that's the expected value. So in a test or in a quiz, most likely in a test, if I ask you find the expected value, this is what I'm asking you to do. So just remember, just like I said last class, which was what, Tuesday? No, I think Monday, whatever day it was yesterday. Pretty much you have to look for the keyword that kind of tell you to direct you what to do. So for this one, as soon as they say expected value, you should already know you have to multiply the x times the p of x. Once you multiply all the x times the p of x, you want to add them up. All right, everybody good for that before we move on down? All right, let's move on down. So the next thing we're gonna go ahead and do, we're gonna go ahead and find the variance and standard deviation for discrete random variable model. So here are the formula. So this is for variance. This one right here for standard deviation. So if you look at both of the formula, what's the only thing different between variance and standard deviation? Start with an S. Close enough. There you go. So the square root. If you look at variance, variance doesn't have the square root. If you look at standard deviation does have the square root. So kind of think about it. If I take sigma squared is equal to 4, if you want to find sigma, let's see if you don't remember square root. What does sigma equal to? Cool, perfect. So you take the square root of 4, which is 2. So that's the only thing different. Variance, you don't take the square root. When you find standard deviation, you do take the square root. Everybody good so far with that? All right, so let's take a look at this formula. So if you look at this part over here, so for that part, all we have to do, we have to get the x value, you square it, and then you multiply by p of x. So this is a little bit different from the mean, because for the mean, you have to get x, multiply by p of x. But for this one, you get x, you square it first, then you multiply by p of x. So for this one, there's like a little layer in between. And then once you get the x squared times the p of x, once you do that for all of them, if you look at the symbol right here, that's telling you to add. So you add all of the x squared times p of x, and then you subtract it by the mean of x squared. So the mean of x is the mean that I found in the last section. So the mean of x is you get the x, you multiply by p of x, and then you add them all. I think that's pretty much it for this formula. Everybody somewhat good for this formula before we go do example? All right, everybody somewhat good for this formula. All right, so let's go ahead and do this formula. So this has to say 2. No. Yes, no. All right, those are just little typo. Don't worry about it. So for this one, it says 4 ticket per customer. So let T be the number of ticket purchased by a random customer. Here is the probability distribution. So the first thing what we want to go ahead and do, we're going to do x times p of t, because the x times p of t, this is going to help us get the mean. So we do 1 times 0.1, we get 0.1. We do 2 times 0.3, you get 0.6. We do 3 times 0.2, you get 0.6. 4 times 0.4, we get 1 point, what was that? 6. Everybody good with those values so far? All right, so you get 0.1 plus 0.6 plus 0.6 plus 1.6. You get 2.9. So the mean of x is equal to 2.9. But if you look right here, we already knew that because we already did this problem. So this is stuff we already knew. Let's do stuff we don't know. Yeah, that's fine. La, 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 la. All right, so right now I'm gonna find t squared. So what's the first t squared? try that again. What's the first t square? 1. So remember, t squared, t is 1. 1 to the second power is 1. What about the next one? What should be my t squared for the next row? Perfect, 4. What should be my t squared for the third row? Oh, we are getting it. What's our t squared for the fourth row? All right. So we get 1, 4, 9, and 16. Everybody go with 1, 4, 9, and 16. So now what we want to do, we want to get t squared, and we want to multiply it by p of t. So let's do a different thing. So we go 1 times p of t, which is 0.1, which you get 0.1. Now you get 4 times p of t, which is 0.3, and you get 1.2. Now you get t squared, which is 9, multiplied by p of t, which is 0.2, and you get 1.8. Lastly, you get 16, and you multiply by p of t, which is 0.4, and that's going to give you, well, I can't really do that one in my head. It should be like 6.4, somewhere around there. Yeah, 6.4. So that's how you get t squared times p of t. So you get t squared and you multiply by p of t. So that's how I got that last column. Any question on how I got that last column? All right, good job. All right, so going back to the formula, if you look at the formula, once I find this, you take the summation. So I'm going to get the sum of t squared times p of t, which is equal to 0.1 plus 1.2 plus 1.8 plus 6.4. So let's add all those up. So 0.1 plus 1.2 plus 1.8 plus 6.4. If you add all of those up, what do you get? You want to double check that. I don't know, double check that. Okay, remember the first number is 0.1, not 1. So for this one, you do want to get 9.5. Does everybody see how I get 9.5 when you add these numbers together? All right, cool. Thanks, Stephanie. So if you look at the formula for variance, all we have to do, we have to get the summation of t squared times p of t, and then subtract it by mu of x squared. So I already know that this value is 9.5 minus the mean, which we found it over here to be 2.9 squared. So if I do 9.5 minus 2.9, so 9.5 minus 2.9 squared, you get 1.09, and this is variance. Any question on how I got the variance? All right, so let's get standard deviation. Because once you get variance, all you have to do is square root our variance. So take the square root of 1.09. If you take the square root of 1.09, you get 1.044. And that's it in regard to how do you find variance and how do you find standard deviation. So variance is this one. Standard deviation is this one. Everybody good on how to find variance and standard deviation by hand? All right, so let's scroll down. All right. So before I show you how to do binomial distribution, I'm going to show you how to double check your answer for this one on your calculator. So let's go to your calculator. La, 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 la. Let's go to TI-84 and turn it on. All right. So what you want to do first, you want to go to stats and you want to go to the edit menu. I want to clear this up, so I'm going to press up, clear, enter. I want to clear this one up, and I want to say clear, enter. All right. So my lists are clear. So for this one, you're going to have two lists. So I'm going to use L1 and I'm going to use L2. L1, you put the X value. L2, you put P of X. So if you look at L1, L1 was 1, 2, 3, and 4. If you look at L2, L2 was 0.1, 0.3, 0.2, and lastly, 0.4. Right. Any questions so far on how to enter the data set? Perfecto. All right. So now what you want to do, you want to hit the stats button again, and you want to move it over where it says calculate. And if you look at number 1, we're going to do 1 bar stats. So if you look at my calculator, you see how it says list and then it says frequency list. So before we used to leave the frequency list blank. In this case scenario, we're not going to leave it blank because now we actually do have the frequency list. Because when you find P of X, that P of X is telling you how frequent does your number occur. So for lists, you leave it as L1. But when you go over here where it says frequency list, you want to change this to L2. So that way it could think X is L1 and the frequency list, which is P of X, is L2. And then you go over here and calculate. And then if you look right here, my mean is 2.9. And if you look right here, my standard deviation, so if you look right here where it says sigma of X, is equal to 1.044, which is exactly what we got when we did it by hand. So if you look at it, this took me like what, 20, 30 seconds to do. So you can always double check your answer to make sure that you did it correct. All right, but that's how you double check it with your calculator. Say if you have like an older calculator, if you have an older calculator, it should look something like this. So it says 1 bar stats. So if you actually enter 1 bar stats, if you look at it, it gives me the wrong answer because it tells me the mean is 2.5, tell me standard deviation is 1.11. And I know all of that is completely wrong. So what I have to do, and some of you are already asking a question about this in the chat, so you want to pay attention to this. Because if you do 1 bar stats, it's only going to look at L1. But if you wanted to look at L1 and L2, what you have to do, you have to tell it. So what you want to do, you want to hit the second button. You want to hit 1, and that tells you to look at L1. But then what you want to do, you want to hit the comma, which is right above the 7. And you also want to tell it to look at L2, which you put second, and you hit 2. And now you have L2. So now instead of it looking at just L1, it could look at L1 for the X value. But if you look at L2 for the frequency list or our P of X. So now if I enter it, now I get the mean, which is 2.9, which that is correct. And I get the standard deviation of 1.044, which is what I got for the correct answer. All right. Everybody good now on how to use one bar stats to check your answer? One recommendation for the people who the calculator actually do it for you, always be mindful because like later on tests and quizzes, you're gonna forget that you have L2 there. So you might want to delete it. For that way, for a quiz and a test later, you don't get that wrong answer just because you have L2 for the frequency list. Because I've seen many students that get the wrong answer just because they left the frequency list as L2, but the problem that they were doing it for doesn't even have a frequency list. So if I were you, I would delete that. For that way, you don't have to worry about like, did I forget to put the L2 and now I'm getting the wrong answer. All right. Everybody good on how to do one bar stat to check the mean and standard deviation? All right, sweet. So let's get to binomial. All right, so for binomial is essentially a shortcut way of how to do the multiplication rule, or not the, the multiplication rule. Because for binomial, let's look at the requirement for binomial. So for binomial, each trial must have two categories for outcome, success, and failure. So if you kind of remember when we were doing the multiplication rule, we were always kind of set up where it was like a success and failure. Okay, if you kind of remember about the baby with green eye, we would say either the baby have green eye or the baby don't have green eye. We didn't really say like, okay, the baby have green eye or the baby have brown eye. We just said like either the baby have green eye or the baby doesn't have green eye. So that would mean that you always have a success and failure. The success will be if the baby has green eye. The failure will be if the baby have anything other than green eye. Next thing, a experiment must have a fixed number of trial. So if you remember when we were doing the multiplication rule and I told you, how do I know when to use the multiplication rule? Like when do we use the multiplication rule other than the event had to be independent? Well, no, because remember, for and, there's technically two different options that we could use for and. How do I know to use the multiplication rule for these independent events? What has to happen? Well, how many random selections should we have? Multiple, two or more. So when it says experiments must have a fixed number of trial, that's what it's talking about. It's saying we have to have a set amount of how many times are we doing a selection. So if you remember when we said we're randomly selected 3 babies, in this case, n would equal to 3 because that's what n is equal, because that's how many times we're repeating this experiment. So if you look right here, it says each trial must be independent of the other, multiplication rule. The probability for each trial must remain constant. P is equal to probability of success. Q is equal to probability of failure. So P plus Q is equal to 1. All right, everybody kind of go with that? All right, everybody go with that. All right, so here goes the formula. Before I show you the formula, I'm going to just go like how we do it with chapter 5 when we're doing the multiplication rule, and then how we could do it now with the binomial distribution. All right, so let's get this new thing going. Okay, 6. Sure, let's do this problem. 58%. All right, so let's do this problem. So it says 58% of children get car sick. If we randomly select 3 children, what are the probability they all get car sick? All right, so let's do this one. So how many children did we randomly select? 3. So n is equal to 3, correct? All right. So for this one, the success is always the probability we're looking for. So are we looking for these children to get sick, or are we looking for these children not to get car sick? Cool. So we want them to get sick. Perfect. So a success would be a sick. All right. So a success in this case will be if the child get car sick. A failure will be if the child doesn't get car sick, correct? All right. So what's the probability this child get car sick? Remember, P is the probability of success. So what's the probability the child get car sick? Are you sure about that? So it should be 0.58. So what's Q? Because Q is the probability that is the probability of failure. So we want this to be a failure. A failure, we already said the child does not get car sick. So what's the probability that the child does not get car sick? All right, 0.42. All right. So X represent how many success do we want? So for this case scenario, how many success do I want? Because if I want all of them to get car sick, that means X should equal to what? 3. All right. Everybody go with that so far? So let's go back to chapter 5.4. So in 5.4, if I wanted to do the problem, what's the only thing I had to do? Like, how can I solve the probability that all 5 or all 3 children get car sick? What can I do? Cool. So you get 0.58 times 0.58 times 0.58. Let's see, what did that give me? 0.58 times 0.58, 0.58. You might want to double check my work. I can't rely on. All right, so if you do 0.58 times 0.58 times 0.58, you get 0.1951. All right, so there's a 20% chance that if I randomly select 3 baby, all 3 of these baby, well, not baby, sorry, child, all 3 of these child will all get car sick. All right, so that's how we used to do it in 5.4. But now in 5, well, not 5, but now in 6.2, we're actually going to be able to do this by using the binomial distribution. So let me show you how to do this by using the binomial distribution. So far, we have this n of x times p of x times q of n minus x. All right, so let's go ahead and do that. So if you look at this portion right here, this portion right there is just a shorthand way of saying it's a combination. So if you remember, we say n is equal to 3, and we said x is equal to 3. So I want in your calculator, do 3C3. So do 3C3 and tell me what do you get. All right, so we got one answer. Cool. So what did the 1 tell us? Okay, what did the 1 represent? Like, it's telling us 1. 1 what? Well, if you remember the combination telling us how many different ways we could get a certain arrangement. So when it says there's only one way, they're telling us there's only one combination that will give us 3, 6 child. Because the only way that all of them get sick is the first baby gets sick, the second baby gets sick, and the third baby get car sick. That's the only way we could get it, where all 3 of them, all of them get car sick. So that's what the NX is telling us. It's telling us, give us all of the different combinations. Okay. What about the P? What does P stand for? Cool. Probability of success. What do we say is the probability of success in this case scenario? 0.58. So I'll drop this down and we'll say 0.58. So we say P and 0.58. And now if you look at the X, what does the X represent? Well, I didn't say what it is. So yes, so it represents the success. So it represents the number of success. So how many success do we want if we want all 3 child to get car sick? So you put 3 right here. What does Q represent? You can either tell me the probability or you can either tell me like what does it literally represent? So it represents the probability of failure, which is the child doesn't get car sick. So that's 0.40 2. So if you look at the n minus x, I'm going to do n minus x over here. In this case, what's our n? All right, so that's 3. What's my x? 3. So what's 3 minus 3? You want to check that math. So yeah, so you get 0 right here. So this is how many failure. So this is telling me I want 3 success and I want 0 failure. And that kind of makes sense because if you look at this, do I see any failure in those 3 numbers? No, they're all success. So this is telling me, this one telling me how many success I want. This is telling me how many failures I want. So what's 0.42 to the 0 power? Cool, 1. So you get 1 times 0.58 to the 3rd power times 1. But essentially the 1s are going to cancel out and you're left with 0.58 to the 3rd power. And is it 0.58 to the 3rd power? Isn't that this? So that's what the binomial distribution is. It's a more organized way to be able to get the probability from when we're doing the multiplication rule. The one good thing about this one, it kind of gives us the opportunity to do a little bit more advanced probability. Because if you kind of remember, like for the multiplication rule, we can't really do it for just one. Like say if I want one child to get car sick, because that one would be a little bit too hard. But for the binomial distribution, you could actually do that for the binomial distribution. So you kind of remember, I kind of want to show you the link between 5.4 and what we're doing in chapter 6. Because when we're doing the multiplication rule, and now that we're doing the binomial distribution, both of them are the same thing. It's just we're using a different formula. So technically, if you wanted to, you don't even have to use the multiplication rule as long as you use the binomial rule. All right then. Any question in regard to that last example? Man, lost a lot of people. All right. So that's going to be it for today. So I'm going to let you know what's going to happen tomorrow.